Hi everyone, nice to know you. Today I'm going to give a brief introduction on convolutional graph neural networks. Convolutional graph neural network is a novel neural network that can be applied to graphs very effectively. Due to the recent advances, convolutional graph neural networks actually have many interesting applications in various domains, such as natural language processing and computer vision. I'll also share some interesting recent research works which I found very inspiring and exciting. I'm currently a fourth year PhD student from the computer science department at Rutgers University. My advisor is Mubashir Kapadia. My research interests are deep learning, computer vision, and graph embedding. The graph embedding is also called as graph representation learning. Basically, we need to learn and vectorize the representation of the graph, or the nodes in the graph, or the edges in the graph. I'm passionate about the next generation machine intelligence, especially machine learning and reasoning over structured data, such as graphs, images, and videos. Particularly, my current research is focusing on first, graph-based modeling and representation learning, and second, predicting spatial temporal sequential patterns. Okay, that's enough about me. Let's start. First, what is graph and why should we consider using graphs? Well, strictly speaking, graph is a general language for describing and modeling complex systems. For example, if you just look at the data on the left-hand side, a bunch of points, which seems to be quite random. However, if we consider every point as a node in the graph, and we add edges to connect those points, we basically get a graph that encodes the relationships of the points. Now, the new representation on the right-hand side is actually much more informative than the representation in the left-hand side. One thing to note is that graph is a type of non-regular structured data. You can consider a sentence as an ordered sequence of nodes or an image as pixel data residing on a rectangular 2D grid map. However, graph is actually much more non-regular and more complex. So yes, graph can encode many useful information and naturally represent many data in the real world, but it is non-regular and more complex. Many real-world data can be represented by graphs. For example, social network. I'm sure we are all very familiar with social networks. We have Facebook, Instagram, Reddit, WeChat, and so on. Social network can be naturally represented by a graph, where nodes are the users and edges represent the relationships between the users. You can also have a bipartite graph where nodes can be the users or the products. You can also use graph to represent a human disease network. A knowledge graph, where nodes are the entities and edges are representing relationships between the entities. For example, here we have this painter and we have Mona Lisa and the relationship is painted. This is the knowledge graph that is often used in natural language processing. There are more types of graphs, of course, such as transportation network, ecological network, package dependency graph, web page hyperlink network, citation network, genetic interaction network, and so on. So now we know that many data are graphs, and the next thing we need to know is what can we do with these graphs? There are several typical ways to analyze graphs. For example, you can predict the type of a given node. And this kind of analytical task is called node classification. You basically want to classify the category of the nodes. You can also predict whether two nodes are linked or not. So whether two nodes are potentially connected or not. For example, in a social network, maybe Linda is following Mike and Mike is following Jason. Then is Linda likely to follow Jason? This kind of question is basically the link prediction task tries to answer. You can also predict the attributes of an edge. For example, there are signed networks. It means that in this kind of networks, each edge has a positive or negative sign. For example, in a voting network, where nodes are the users, and the edges can have positive sign or negative sign. And the positive sign basically represents supporting the candidate user, and negative sign represents opposing the candidate user. So when given two user nodes in an ordered way, you need to predict the sign of the edge. And this is the edge sign prediction task. You basically want to predict the attributes of an edge. Given a graph, you can also do community detection to identify those densely linked clusters of nodes. Given two graphs, you can do network similarity comparison to find out how similar two networks are. I'll give more details on two tasks. First is the node classification task. For the node classification task, the input to the machine learning model is basically the full graph structure and the class labels of some nodes. So those colored nodes means that those nodes have their class labels, and different colors represent different categories. And for those green nodes with a question mark, basically means that for those nodes we don't know their category information. And the model needs to predict the class labels of those remaining green nodes. So the output from the machine learning algorithm will be this. So the graph structure is null, so it does not change, but now we will know all the category information. One notable example is to classify the category of paper for a citation network. In a citation network, nodes are basically the papers, and the edges represent citations. And each paper can belong to a subject category. For example, here we have learning theory, we have text mining and information retrieval, we have social and information networks. Those are different subject categories. So each paper can belong to one subject category, sometimes multiple. But it is possible that not all papers are labeled with this category information. For example, in this image, those white nodes are basically unlabeled nodes. So we don't know the category information of those white nodes. And the model needs to predict their categories. For link prediction, usually there are some hidden links. For example, those edges are basically hidden they have like question marks, so we don't know whether these two nodes are really connected or not. And the machine learning model needs to differentiate these true hidden edges. So these two are actually true hidden links, and this one is actually false edges. So the machine learning model needs to differentiate these true hidden links from some false links. So this is the link prediction task. That means in the beginning, the input graph is actually not full, so the structure itself is not complete. And this is one application of link prediction. So given a bipartite graph where nodes can be the drugs or disease, so link prediction predicts which disease a new molecule might treat. So the edges are basically trees relationships. So graphs are useful in many scenarios and tasks. But why deep learning on graphs just became popular in the last few years? And in other words, why it is challenging for deep learning methods to work on these graphs? Well, this is because modern deep learning toolbox is actually designed for grids or simple sequences. So as we mentioned before, images have 2D grid structure. So this is an image. It's basically having this kind of 2D grid structure. And because of the regular structure, we can design convolutions. Text and sequences are basically have linear one-dimensional structure. And because of this kind of structure, we can basically define sliding window, recurrent neural networks, and so on to handle this type of structured data. However, graphs are actually far more complex. So graphs have arbitrary size and a complex topological structure. One node can be connected with thousands of nodes, and another node might just connect with 2 or 3 nodes. The structure of graph is arbitrary, not regular. In addition, there is no fixed node ordering or reference point. Nodes and their neighbors constitute a set. All permutations of them are actually equivalent. Unlike image data, you cannot permutate neighboring pixels of a given pixel and still obtain the same image. In graph, all permutations of nodes and their neighbors are actually equivalent because they constitute a set. Graph neural networks are designed to address those challenges. So the abbreviation for graph neural networks is GNN. GNNs automatically learn features or representations of the nodes, and perhaps also the representation of the edges. The learned representation will basically capture both of the structural information and semantic information of the graph. And those learned representations are particularly suitable for downstream machine learning tasks, such as node classification. So just like CNNs are the typical deep learning approaches for images, GNNs are the deep learning approaches for handling graphs. GNNs perform graph representation learning, and the goal is to learn a mapping function f. And this mapping function f can map every node to a d-dimensional feature vector. And this d is usually much more smaller than the total number of nodes in the graph. So usually, even for small graph, sometimes we have thousands of nodes, and the output from the GNN is actually only like 64 dimensional vectors or 256 dimensional vectors. So this d is usually much smaller than the total number of nodes in the graph. And these learned d-dimensional node embedding vectors can basically be the feature vectors of the nodes and input to some machine learning methods. For example, here d equals to 2. So given this disease similarity network as input, we learn this mapping function f through GNNs, and the output are basically the two-dimensional node embeddings. Given these two-dimensional node embeddings as input to other machine learning methods, we can perform many interesting downstream tasks. For example, Here, since the dimensionality is 2, so we can simply visualize the nodes in the embedding space. And some nodes with similar semantic information will be clustered together. So yeah, of course, we can use these node embeddings to perform clustering. We can also use those node embedding to do node classification, name prediction, and so on. So the goal for GNN is to learn this mapping function f. GNNs have many advantages over other techniques in graph representation learning. And the most important one, in my opinion, is basically the generalization ability. So a GN model is learned from one graph, but it can be applied to a new graph without hurting too much of the performance. So without any training, the learned model, which is learned from another graph, can be applied on a completely new graph and still do the downstream tasks. GNNs are also very efficient and effective, and GNNs have been applied to many domains. Recent graph neural networks generalize convolutions to the graph domain, so that's why it's called convolutional graph neural networks. So if you are very familiar with convolution layers in convolutional neural network, convolution in GCNs is basically the same operation. GCN themselves can be categorized into two major algorithms. One is spectrum-based method, the other one is called spatial-based methods. Spectrum-based approaches usually define graph convolution by introducing filters from the perspective of graph signal processing, where the graph convolutional operation is interpreted as removing noises from the graph signal. They usually have a very solid mathematical foundation, and they often rely on the normalized graph Laplacian matrix. They depend on a fixed graph structure heavily. The second category, spatial-based methods, they usually define graph convolution based on a node's spatial relations. So images can be considered as a special form of graph where each pixel representing a node. So those methods inherit the ideas of information aggregation, or called message pathing. Those methods inherit this kind of ideas to define graph convolutions. Spatial-based methods have developed rapidly recently due to its attractive flexibility and generality. Let's first do some recap. Convolution in CNN refers to multiplying the input neurons with a set of weights that are commonly known as filters or kernels. The filters act as a sliding window across the whole image and enables CNNs to learn features from the neighboring cells. So given this filter, the filter will be applied across to the image as a sliding window. And this filter, the numbers in the filter are actually learned by the model. These are actually the learnable parameters, the weights. Within the same layer, the same filter will be used throughout the image, and this is referred as weight sharing. For example, using CNN to classify images of cats versus non-cats, the same filter will be used in the same layer to detect the noise and also the ears of the cat. GCNs perform similar operations, where the model learns the features by inspecting neighboring nodes. The major difference between CNNs and GNNs is that CNNs are specially built to operate on regular Euclidean structured data, while GNNs are the generalized version of CNNs, where the number of nodes and connection varies, and the nodes are unordered. Basically, graph is irregular and is non-Euclidean structured data. So as illustrated in this left image, each pixel is directly connected with its nearby pixels. This is the central pixel, and given a 3 by 3 window, the neighborhood of this pixel is basically the surrounding 8 pixels. A filter is then applied to this 3 by 3 patch by taking the weighted average of pixel values of the center node and its neighbors across each channel. So the weighted average of these 9 nodes are actually computed. This is the convolution layer in CNN. Convolution in GN is illustrated in the right. Similarly, the spatial-based graph convolution convolves the center node representation with its neighbors representation. For example, for this red node, we have these 4 direct neighbors, one-hop neighbors. So the spatial-based graph convolution convolves the center node's representation with its neighbor's representation to derive the updated representation for this center node. Now I'm going to quickly review the basic mathematical details of spatial-based GCN. GCNs are usually constituted by stacking multiple GCN layers. A GCN layer is basically performing message propagation and updating on the nodes. The general GCN message passing rule at layer L for a random node I consists of 2 steps. The first step is called feature transformation. So given the feature vector of node I passing as input to this layer, so that's why here is L minus 1. Learnable weights and bias. So this W here means the weights parameter of this layer L, and B is the bias parameter of layer L. Those parameters are learnable. So learnable weights and bias parameters are used to perform the transformation. So output is this MIL. This is the transformed representation of node I after the first step. The second step is neighborhood aggregation. So transformed representations of node I's neighboring nodes, including node I itself, where so here J can be node I itself or neighbors of node I. So this means the set of neighbors of node I. So for each, so we aggregate this transformed representation of node I and node I's neighbors with this weighted sum. This Wij is basically the aggregation width, and this aggregation width can be computed with different mechanisms. The simplest one is to directly use the adjacency matrix, maybe, and then you can use other mechanisms such as attention to compute this weight, the aggregation weight. Then, after we get the weighted sum, a non-linear activation function here, a possible one is ReLU. This kind of non-linear activation function is then applied on the aggregated representation, and the resulting representation is the output feature representation of node I of this layer L. So these 2 steps form the message passing rule of spatial-based GCN and are performed for multiple layers to propagate messages over their neighborhoods, including this one. So multiple layers are stacked together. The output from the last layer is the learned feature representation of each node, which can be used as the input to other machine learning models, such as multi-layer perceptron, to perform many other downstream tasks. GCNs leverage node features and can be applied to unseen graphs in inductive settings. I would recommend reading this blog, Understanding Graph Convolutional Networks for Node Classification. So if you have time, please take a look if you are interested in GCNs. Okay, now applications. GNs have received a lot of attention and progress in the last several years. One future direction of GNNs is to apply them to new problem domains, instead of just working on those basic tasks like node classification and link prediction. And GNNs did not let people down. GNNs have been applied to many domains, including chemistry, physics, social sciences, knowledge graphs, recommender systems, neurosciences, and so on. You can also check out this blog, Top Applications of Graph Neural Networks 2021. Here I listed several novel applications that I found very interesting and inspiring. I'm going to briefly introduce them. First, GNN for image recognition. These two datasets, these two are actually two classic image classification datasets in computer vision. Recently, researchers have converted these two original image datasets into graphs using superpixels. So this is an example. So this is original image, and this is its corresponding representation using the superpixels. And the task is then to classify this superpixel-based graph into their corresponding image category. So for each image example, those researchers, they built a k-nearest neighbor adjacency matrix based on the 2D coordinates of the superpixels. So here in this figure, these are the graphs by using the 8 nearest neighbor. So this is the example image, and this is the corresponding superpixel graphs. The node colors here basically denote the mean, the average pixel intensities. These researchers have applied several GN methods, such as GCN, GraphSage, GIN, DeepPool, GAT, MoNet, and so on. Several popular famous GN methods to perform this image recognition task. And the results are actually pretty amazing, quite comparable to standard methods. GNs can also solve combinatorial problems. This traveling salesman problem, TSP, is a well-known combinatorial optimization problem, and it has been intensively studied. To solve this problem, you basically need to answer, given a list of cities and the distance of traveling from one city to another, what is the shortest possible route that visits every city and returns to the origin city? To solve this problem with graphs, researchers have posed the TSP problem on random Euclidean graphs as a binary edge classification task. So the ground truth value for each edge is whether the edge belongs to the optimal TSP tool or not. So this is a binary edge classification problem. We transform the original problem into a binary edge classification task. Moreover, GNNs can benefit many complex computer vision tasks, for example, human action recognition. This task aims to predict the action type of a person in a video. For example, for this input video, the action type is basically running. Researchers have approached this task with GNNs. For example, authors of these two papers. They first estimate the human pose in every frame. After you estimate the human pose, you basically get a skeleton graph like this. So considering the temporal domain, you basically get a temporal skeleton graph. And these researchers propose some different types of temporal graph convolutional networks to solve these tasks. So after transforming the original input video into the temporal skeleton graph, you can just use those temporal GCNs to learn the representation for like each node, and aggregate them. You basically get a representation for the input video, and then you can perform the downstream tasks such as action classification. And this second paper also consider the multi-scale features. Basically, like these three nodes actually can be considered as another more coarse scale hypernodes. This kind of idea. This CVPR20 paper uses a GNN for the action segmentation task. Action segmentation task basically, given a video, you need to temporarily localize the actions performed in the video. For example, this video, maybe in the first several frames, in the first 3 minutes, maybe 3 minutes too long, 3 seconds, it's like the action is take bottle, and then the later action is pour water, and in the end of video the action is put glass. So to solve this task, you basically need to temporarily localize the actions performed in the entire video. So authors of this paper, they first use a backbone model which can produce some initial results. And here is basically the initial results produced from this backbone model. And then they basically consider each initial predicted action segment, like take bottle, pour water, this action segment as nodes. They consider those initial predicted action segments as nodes. And then we basically have like fully connected graph. And these fully connected graphs are defined to model and reason the temporal relations of all the action segments. Since now the edges basically connects two action segments, so this with some as we are learning the representation for the graph, we are basically trying to perform some relational reasoning. Yeah, so after we use this kind of graph idea to do the relational reasoning, the prediction results will be refined. So this will be the final results from their methods. And this AI21 paper shares a similar idea. They also use GNN to refine the prediction from a backbone model. But now, the difference is that now each frame is considered as a node. And the GNN is used to model the long-range dependency between the frames and at multiple time spans. For example, not every node is a frame now, and for this node, its neighbors are basically nearby 2 frames, but at a second level, for this node, its neighbor now becomes into this one and this one. Yeah, so this is how they handle the long-range dependency between the frames, and this is how they use the multiple time spans to better model the temporal relationships of the frames. Since GNNs can model and read the relationships, an actor relation graph is also learned for the group activity recognition task. The idea is to let the model to focus on the interaction between the people. For example, here we basically use some feature extractor to first get the representation of each person, and now each person is considered as a node, and we want to use the graph to focus on the interaction between the different persons. By focusing on the interaction between the people, we can better predict the group activity. And of course, GNNs can learn human-object interactions. By considering human and object, so human and object as the nodes. This is how we can construct the graph, and the potential interaction. Any potential interaction will be considered as the edges, and the edges, the relationships between the entities will be refined in this message passing process. Graph RCN is also proposed to generate the scene graphs for the images. Basically, we can first have extracted sets of objects from an image by using some backbone model, and now each extracted objects will be considered as a node, and the graph is fully connected in the beginning, but the edges are later prompt by the model, and in the end we can do node classification and edge classification to predict the actual type of the nodes and the interaction type. GNNs have also been applied to face parsing. So this is an input image, and this is parsed face. This is a bit similar to the superpixel-based graph for image recognition. So here, a collection of pixels with similar features are projected to nodes. So each node is basically a pixel region, and those pixels share similar features. And the model learns and reasons over relations between these pixel regions. This AAAI 20 paper uses GNN for the crowd counting task. Here, the feature map from the CNN backbone is considered as the node. Particularly, multiple scales of feature maps are generated, and each scale of feature map is a node, and the graph is fully connected. Okay, I'll stop sharing novel applications of GNNs. I really found those papers, those research works very interesting and amazing. Myself, I've been working on GNNs and computer vision for a while, and these are some of my papers that are sort of related to today's talk. For example, in our team, we have considered a floor plan as a graph, where each room is a node and the edges represent the room connectivity. We have also performed a video reasoning task with a novel transformer model. And an implicit graph is actually constructed by the transformer model, and basically each node is the object, and the transformer model can model the object interactions. Currently, I'm working on graph-based relational modeling for video representation learning. So if you find my talk interesting, if you hope to work with me, or if you come up with some new ideas that I might help with, please just drop me an email. By the way, my name is Hongwu Zhou. Thank you for watching.